In this video, I will explain you the variation of current and application of transformer and losses in transformer. Now, we have got the equation that ES divided by EP is equal to NS divided by NP. Now, EP is the EMF applied across primary and ES is the EMF in the output, that is across in the secondary. NP is the total number of turns in primary and NS is the total number of turns in secondary. This is the equation. Now we are going to take an important assumption here, that is law of conservation of energy. See, law of conservation of energy is true, it's not an assumption, but here in this case it is an assumption. I will tell you why. See, we are going to consider that whatever the power input we are giving at primary, that would be received at the secondary. But this is not true actually. 90% would be delivered. The reason is there is the conversion of one form of energy into different form. Now here the current is in the circuit in the primary, and this is now given as the magnetic flux, and now this magnetic flux have to do a work at this secondary. Now here there would be a conversion, right? See, out of 100 joule input, we won't be getting 100 joule in the output. Correct, a part would be lost, and I will tell you how this energy would be lost. There are 5 different types of losses in transformer, but now we are going to consider that none of these losses are present, so that whatever the energy or power we are giving at input, that would be there in the output, which means efficiency is 100%. There is no losses. Okay, now in that case, power input or at primary is equal to power output, that is in the secondary. Now what is power input? I primary into V primary. What is power output? V primary or E primary? Okay, so I will take it as E primary, as I have used E here. Now power output is I secondary into E secondary. Now here we know what is ES by EP, right? So I will take ES to this side. ES by EP is equal to IP by IS. See, now this is equal to NS by NP. This is transformer equation. Now this equation can be applied anywhere, okay, with no confusion. But to apply this equation, that is to bring the ratio of current here, check in the equation, is there 100% efficiency mentioned, or if there any sort of losses mentioned. If the efficiency is 100%, then definitely you can take IP by IS is equal to ES by EP is equal to NS by NP. This equation anyway you can apply anywhere, but if the efficiency is given, then you can't equate this equation. IP by IS equal to ES by EP. Now if efficiency is given, efficiency is 80%, means power output divided by power input. Now what is power output? This is power output, ES into IS. Now what is power input? IP into EP. Now this is 80%. 80% means 0.8. Now I can say from this equation, ES by EP is equal to, keep ES and EP here, that is equal to IP by IS into 0.8. See, when the efficiency is given and when we substituted the value, it is not equal to, ES by EP is not equal to IP by IS. That is equal to IP into IS into efficiency. Now when efficiency is given, ES by EP is equal to IP by IS into efficiency. So efficiency should not be taken in percentage. 80% if it is given, you should only take 0.8. Okay, so the maximum value of efficiency would be 1 and least value would be 0. So this equation you can apply anywhere, okay, where efficiency is given. If efficiency or about losses, if nothing is mentioned, then you can take consideration of this equation. Okay, now I will tell you why we are using transformer. Now we know that when power from powerhouse is sent to for the house appliances, so powerhouse would be kilometers and kilometers away from our house, let's say 500 kilometers. Now across this 500 kilometers, the only connection is the copper conductor, or the only path that delivers power from powerhouse to our house appliances is nothing but a copper wire, right? Now the current has to pass through this copper wire and reach our house. Now whenever current is passing through copper wire, there would be losses, right? I square RT, this much would be the loss. So whenever I amount of current is passing through a copper wire, there would be a loss of I square RT. Now as it is measured in kilometers, then the resistance of this copper wire would be very high, and anyway this is not copper wire which we are using aluminum wire, because copper is expensive. Now the resistance due to that would be very high, so that this loss would be very high. So see, let's say when we are sending 1000 watt from powerhouse, then the loss would be around 600. So after a loss of 600 to 700 watt from the power supply, the only deliverable is 300 watt. See, to deliver 300 watt, we need to spend 600 to 700 watt as power loss, and that too from an input power of 100 watt. So how to reduce this power loss in transmission? Okay, so this can be reduced by simply reducing the value of current. Now we know that the rated power, so when we are delivering power from powerhouses to house applications, right? So 1000 watt, this much power has to be delivered across kilometers. So power is nothing but V into I is power. So let's say power that have to be delivered is 1000. Now I can choose voltage as 100 and current as 10, and that will become 100 into 10,000 as the power transmitted. Now when I am using in this way, then the power loss would be I square RT, and that would be 10 square, that is 100 RT. But at the same time, if I am using this as 10 as voltage and 100 as current, then I square would be 100 square RT, so that would be 10,000 RT. See, the loss is more. Now it is better to reduce voltage, better to increase voltage so that the current would be decreased accordingly. So the 1000 watt, if I am planning in this way, that current is made to 1 ampere and voltage is made to 1000 volt. Still the power carried would be 1000 into 1, which is 1000 itself. Now what would be the power loss? I square RT would be 1 square RT, which is RT. See, it is neither 10,000 RT nor 100 RT, it is 1 RT. So during power transmission, we will increase voltage into around 11 kV or above. So voltage would be increased to such a high value so that we can reduce the value of current transmitted. So accordingly, the value of power loss during transmission will be less. So this is the biggest purpose of usage of transformer. So from powerhouse, what we will do, we will step up. So from powerhouse, we will use a step up transformer. So step up means in primary windings would be less, in secondary windings would be more, so that the power is stepped up to a higher value. Okay, now this is high voltage 11 kV, but this cannot be used at home applications, okay, appliances. Now this before delivered to house, this would be step down. How? From using a step down transformer having more number of turns in the secondary as compared, sorry, in the primary as compared to the secondary. So this is step down. So from powerhouse, it is stepped up to 11 kV. Now the 11 kV supply at the nearest distribution center, that would be stepped down to a lower value, which is 200 volt or maybe less. Generally it is 200 volt, so that this power loss during the transmission can be minimized. So that is the application of transformer. Now we will see what are the losses in transformer. First thing is flux loss. See, here we have considered that power input is equal to power output. That is not 100% true. There would be certain types of losses in transformer, so that the power output would not be equal to, would not be 100% equal to power input. Maybe 90%, that will be true. Okay, so one thing is flux loss. We are assuming when we have derived the equation for transformer that the entire flux generated by the primary is being linked with the secondary, but actually it won't be in this way. So there would be flux linkage through the other side as well. So there is no 100% linkage of flux produced by primary on secondary. Okay. Iron losses. Iron losses are nothing but eddy current losses. Whenever flux produced by the primary is linked with the soft iron core. Soft iron core is basically a conductor, right? So what will happen? See, the flux linked with this conductor, the metallic core is changing. Now whenever flux linked with the metallic core changes, there would be, you know, form eddy created by electron. These are called as eddy current. So inside there would be eddy current. Okay, now this eddy current can be minimized by, you know, laminating this sheet. So a big core would be cut into, you know, number of laminas, and you know there would be dielectric field in between two laminas. So this is one lamina, one paper, and see one paper, one lamina can be considered as one paper, next lamina, next lamina, next lamina. So that, see, here in between lamina there would be a dielectric, okay, an insulator. Then comes the next metallic lamina, then an insulator. So you can see that here there is core, but now only this is area that has conduction. In between, that has the property of conductivity. In between we have dielectric, next element, and we have dielectric in between. Now see, for eddy current previously it was a one piece in this way, so it can easily form an eddy current loop in this way. Okay, but when we are making into number of laminas glued together with a dielectric, see, it is very difficult to form. Now if this is the thickness of one lamina and next one dielectric, then next lamina, then comes dielectric, then next lamina, so it is very difficult to form eddy current in between, because the reason is this area of cross section is very less, and we know resistance is equal to rho L by A. So when area of cross section is less, then the resistance would be more. So this would be a high resistive path to form eddy current, so that eddy current losses can be minimized. And next way is, instead of making in this way, we will increase the total area to this also, so that now, you know, for the eddy current to form, it has larger length. So increasing length also will increase the resistance. So one thing is, you know, lamination, that is, you know, these laminas are glued together with insulator. Next thing is, instead of using core in this way, we would make core in this way, and the winding would be done here, so that for an eddy current loop it have to make a loop with longer length, where resistance would be long, so eddy current losses would not be much present in that scenario. Next thing is copper losses. Simply, whenever current is passing through the copper conductor, there would be I square RT losses. the one which I have told in the case of power transmission. So this is copper loss, I square RT loss. Hysteresis loss. Now what will happen with this core, with the ferromagnetic core? That will continuously magnetize, demagnetize, magnetize in opposite direction, right? See what will happen? See, initially when you are increasing the current, this will magnetize, then demagnetize and magnetize in opposite direction. So after each circle, this much amount of energy is lost. This is called as this is called as hysteresis loss. This happens because this inner core is continuously magnetized and demagnetized and oppositely magnetized. This we have learned in chapter magnetism and matter. Go back and check that lectures. Okay, next one is copper loss. Now what is copper loss? I have told you there are multiple laminas glued together to form the core. So you can cut a rectangular piece here and that can be an illustration for the core. Okay, now see, whenever these are magnetized, this will become north, this would become south, this would be north, this would be south, this would be north, this would be south. So what will happen now? Whenever they are magnetized in the same direction, north south north south north south, so which means these laminas will come together. Now whenever they demagnetize, they go back. Okay, there won't be any kind of magnetic property. Now whenever they magnet, north south north south, so what will happen? These glues come together, then repel. No, they go back to initial condition, come together, go back, come together, go back. So this will happen the frequency number of times in a second. Okay, so see, it's a clapping sound. Okay, whenever we pass near to any transformer, we can listen to those sound. Okay, some this kind of some boom sound we can see, a frequent sound. So that is sound loss due to continuous magnetization and demagnetization. So these losses are very important: flux loss, iron loss, copper loss, hysteresis loss and sound loss. You should be able to explain in detail about this kind of losses. Okay, thank you.